Okay, hello, good morning everyone. Welcome to day 3, hello there. Welcome to day 3 of the Chaos Communication Congress here in Berlin in the BCC. I'm glad someone did show up tomorrow on the third day. All of you, I'd like to thank you from Berlin for the hospitality we're experiencing here. Okay, so it's just a personal note. Okay, we start off today with some Wi-Fi optimization, especially IEEE 802.11e, so it won't be of any help here. Your slow wireless will stay slow, but hopefully when this approach comes through next year, we maybe have a faster wireless, but you need to purchase a new card. The talk will be held by Achim Friedland. He's currently studying computer science at the TU in Ilmenau. And this talk is from a work he had to do for his studies. Okay, so just give it up for Achim Friedland.
Yeah, good morning everyone. Welcome to my breakfast lecture. I hope you all sleep well. I will talk about optimization for your Wi-Fi. This is not really intended for normal Wi-Fi in a hotspot or something else. It's more intended for point-to-point links and mesh network based on Wi-Fi. So, the outline. I will talk a bit about the standards of 102.11. I will later on go on some performance optimizations and give short conclusions and prospect on future work. So let's start with some motivations. Why you could do this, what I did. There are, first of all, perhaps the academic motivations. You have to do something when you are studying. And there are a lot of nice ideas. Perhaps you have a university campus and there are a lot of buildings and a lot of non-university buildings in between. You will have a problem, internet access in a faraway building, maybe on the one hand slow or expensive to get, because you can't have fiber optic link to every building. Perhaps it's a better idea to have Wi-Fi, because Wi-Fi can give a quite sufficient and cost-effective internet service. Once you have used point-to-point Wi-Fi links, there are perhaps better or more interesting ways to play with this technology. There are a lot of ideas how to build mesh networks. The word mesh is more or less just, it's a piece of bullshit bingo. Every kind of non-so-blunt network today is called mesh network. We have to look at this in detail later. The academic excuses why to do this are mostly, we can improve performance or robustness or something else. At least we can do some optimization. There are other motivations perhaps. The internet infrastructure, is mostly brought to you by ISPs. They are hierarchical and controlled more or less centrally. There are a lot of internet exchange points. They are very centrally organized, and you never know when there is a problem in society. Will the DX6 really run at this moment or not? So, yes, at the moment, perhaps even our society has some problems with democracy. And in this case, even the other projects, the overlay networks, YAP or Tor, they are really cool and nice projects. They will give you confidentiality and integrity, but there's another part of security. It's called the availability. And yes, they are overlay networks, and they need a network under this technology, so perhaps they may not work all time. There are some related works to my work. There are a lot of different projects and ideas how to build point-to-point or mesh networks. You all should know the Freifunk.net people. They are building huge and well-optimized mesh networks. They are quite a bit different from the networks I will talk about. I will give you the differences on a later slide. There are academic projects with newer ideas how to build mesh networks like the MIT RoofNet. And there's even an upcoming IEEE 800.11s standard for mesh networking. This is also not quite the kind of mesh networks I will talk about. Yes, all these networks together have still some problems. They are quite nice, but even the Freifunk people know OLS-Air is a very nice solution, but perhaps not the best. They are at the moment designing a new protocol. It's called Batman. Perhaps someday there will be a talk about this from the Freifunk people. And let's look at the Wi-Fi scenarios I'm interested in. They're basically the normal long-range point-to-point links and mesh networks. As you can see on the right side, there are different colors for every link between mesh nodes. This should represent different channels. I personally don't think it's a good solution to have a flat network like the Freifunk people, so that every node, every link uses the same channel. This will limit the throughput and increase the delay. It's more complicated to have different channels, but perhaps someday, in some years, we have some good ideas how to solve these problems. We are also not interested in the legacy 800.11 standards. The B standard might be a quite good standard for building long-range links, but there are more interesting features in the 800.11e standard, mainly in the medium access code, not in the layer 1 part of this standard. The main problem for 800.11 was, it is still, it's mainly designed for much more than 2 people, mainly for use to be used in a hotspot. It's designed to support short distances and a lot of frame errors. And even more or less, it's designed to work indoors. When you look at the new standard 800.11n, the real throughput gain can only be, you can only get real 600 megabit of throughput if you are indoor. In outdoor scenarios, this won't be possible. Point-to-point links or point-to-point links used in mesh networks, this assumption is changed, and we have to look at them and the functions of these parameters a bit more in detail. So the first thing you will experience of Wi-Fi is, okay, the throughput and the delay might be okay, even compared to DSL, but compared to normal wired internet access, it's really slow. So perhaps you will just say, oh, let's do the Cisco way, use more bandwidth. But there's the questions how to use it clever. Perhaps it's not really useful just to double the bandwidth, like Atheros does at the moment with its channel bonding service. We will see that this is a nice solution, but won't increase the throughput really dramatically. We could also use a normal channel bonding. This is simply to use two channels and use a round-robin service or something else to send one packet on this link and another packet on the other link. This is perhaps also quite a nice solution, but it will have problems if both links have different failures or different delays and so on. It will be quite difficult to use an adaptation layer to hide this hardware problems to the higher layers. So another solution, a solution not really new, but perhaps the effects are quite interesting, are directed radio links where you use two channels, one for the upstream and one for the downstream. It's quite the same like your Ethernet does with full duplex. You have one pair to send and one pair to receive. But in the wired internet, it's not really, the improve is nice, but not really dramatically. In the wireless world, there are quite interesting effects of this technique. As I said, doubling the bandwidth is a nice idea, but it's very interesting. This will only increase the throughput by about 41%. This is not really cool when you think you use 100% more bandwidth, but only get 41% more throughput. What is frame bursting and aggregation, we will see soon. The channel bonding, as I said, it's quite complicated. This complexity will also limit the throughput. And the most interesting thing is at direct radio links there won't be any concurrency. Even on point-to-point link, you have two users and they will fight for channel access. This can be solved, and we will see that this will have really interesting effects even on TCP. And for all these methods, you could use the 800.11e quality of service parameters and optimize them. That's a really rough overview about the Mac. Here you can see. Oh.
Good morning. The next talk will be about unlocking file vault, the encrypted file system in Mac OS X computers. All of you Mac users probably know this. Besides the fact that they claim to
Yes. Okay. The basic access method used in all wireless standards is, just look at the medium. If it's busy, wait until it's free. Wait a different time. It's called a distributed interframe space. It's just some time. Then you have the contention files. There you wait different time slots. The actual number of time slots you will wait is random. So if you have multiple stations who want to access the channel, they probably will have or will choose different random numbers, and so not every station will access the channel at this point at this quite same point of time. So you have a bit controlled the channel access. Okay, when the data frame was received on the other side, you will process it, and after a short time, you will send an acknowledgement back. This is rather simple, I think. The actual time you are in the contention phase is a random number between two parameters. This is not really interesting at the moment, but we will later see if this phase can be optimized. At the end of every successful transmission, you have another contention, so that the station who accessed the channel this time won't send immediately the next frame, but will wait a random time and let other people try to access the channel. In 800.11e there is another idea. It's quite unoptimal to send only one frame. There's the possibility of frame bursting. It's basically sending multiple frames back on back, just separated by a short interframe space, and so you will have only one time the contention, and if the station gets the channel, it can send 5 or 10 or 20 packets. This will increase the throughput, as we will see shortly, significantly, but it will also increase the delay because it takes longer time for the other stations to access the channel again. This method, or the duration and single station can access in this channel, is called the TX opportunity. It's a specific amount of time which is normally defined in the access point and sent to the clients so that they know how long they can actually access the channel. Okay. There's also a new method on acknowledgement, on sending acknowledgements. In the normal access method, you had to send an acknowledgement for every frame, but now you can combine several frames and send one block acknowledgement. This will save a lot of time and will also increase throughput and decrease the delay. Okay, it looks quite difficult, but the main details you should see. 800.11e defines 4 priority queues. It's mainly for different kinds of traffic. You have the background traffic, best effort, video, and voice. And all parameters of the 800.11 medium access code can be controlled within these different queues. So you can differentiate the video, give them a high priority over best effort traffic and so on. The main parameters of interest is the interframe space at the beginning.
So we're going to talk about what FileVault is, and we're going to talk about problems that other people have found and that we found with FileVault.
Yeah, it's the interframe space at the beginning. As you can see here, voice and video are perhaps have the same access delay at the beginning. The best effort will wait some time longer, and background traffic will wait a rather long time. Even the contention phase, the minima and maxima of your random numbers can be controlled so that voice has quite a small random number, and background traffic there's a really big random number. And perhaps it's also interesting, there is the possibility to tag a class to send no acknowledgements. This could be nice for some people, but most of the time this won't give you really throughput increase, because there are a lot of errors on a Wi-Fi link, and you probably want to have a fast acknowledgement and fast retransmit mechanism. So, as I told you, the interframe space influences mainly the access delay before sending a VLAN frame. It should be clear, this is very easy to optimize, just make it smaller. The CVmin influences the collision probability when the number is very small. There's a high probability in that different stations will choose the same random number, and if it's very high, it's not so probably that there will be a collision. But when the number is very high, the delay to access the channel will increase. This is okay, somewhere an optimization problem. What's the best range for your random number? There is a CV max. This is a detail of the medium access code. You won't, with every retransmission, you will increase the size and the range of your random numbers. This is really useful in a hotspot scenario, but it's not really useful on a point-to-point or mesh network. So you can just set the CV max to the CV min value and live with this. Sorry. And the TX op limit is also a candidate for optimization. When you are able to send more packets back on back, you will probably increase the throughput, but also increase the delay. And so there is probably some good value between the min and the max value, so that you can live with the delay and also can live with the throughput. In the new standard 800.11n, there is another solution. It's called a frame aggregation. It's quite the same like frame bursting, just it removes the interframe space to very short MPDU delimiters, and the possibilities to aggregate different kind of frames are much better. But it's not really something really interesting. Yes, this will increase the throughput really dramatically because there is no waiting time, and on long range links this interframe space won't be increased. So it's, as we'll see shortly, it's really a nice standard. And as you might know already, on long range links you have to change a few parameters to make this work. It's more or less a time slot for waiting or the interframe spaces and the acknowledgement timeout. But this is really easy to do and should be possible with, I think, every VLAN chipset. So more interesting, some graphs. If you have a normal alt access method, yes, you won't have the, down here. This is for 800.11a or G. It's not really quite interesting. It's slow if you use, at this point, frame bursting. You will see when you send 2 frames back on back or 10 frames back on back, the throughput will increase, but soon there will be some kind of saturation. So it doesn't make any sense to send 30 packets back on back. It just will increase the delay, but the increase and the improvement of throughput won't be really noticeable. On 800.11n, we also see the medium will, or the standard says, this is a 150 megabit channel, but you will see you're probably by 47 megabit on a single channel using one stream or without the MIMO. This is, quite frustrating. You buy a new standard, they will tell you, hey, even without MIMO, you will have 150 megabits, but it's not really a difference between the old and the new standard. But if you now use frame bursting, frame aggregation, and so on, you will see the throughput will increase really dramatically. If you see here, perhaps at 10 packets back on back, it's a really dramatic difference between this 47 and something, I think about 100 megabit. So even when you send really a lot of packets, perhaps, let's take 25 or so, compared to 30, you will also see an increase in throughput. It's you have to decide what you want at this point. Another graph, when you see the distance, you want to have your point-to-point link, and the throughput. The throughput will also decrease with the distance, and this is because the optimizations you do with the acknowledgement timeout and the interframe space, the throughput will decrease very fast. The different colors I will explain later. But using these frame aggregation technologies, you will see the throughput will stay much more stable, even on long-range links. And so it would be perhaps a good idea to use all this and build a nice, cool point-to-point link. When you do simulations, yes, it will be quite interesting to look at the distribution of delay between two packets. As I told you, two stations who want to access the channel just choose a random number, and who got the smaller number will immediately access the channel. This sounds really easy. But actually, if you implement this and do some simulations, it's very interesting when this is the time and this is the probability when there is a channel access. The delay spread is really quite complicated. You won't really be able to say when there's a high probability that a packet will be transmitted. This, as we will see later, will have an enormous impact on quite a lot of protocols who are using a smooth round-trip time. And the round-trip time will be influenced by the delay of the packet and the channel access. And when you have such a curve, which will represent for a special channel here, 54 megabit channel, the delay spread, and you will just use the median or something else to get a value. Perhaps, I think the median would be about here. And even you use a smooth round-trip time, you may imagine this value won't be very accurate. And this will influence the measurements. And perhaps someone in the audience might know where a smooth round-trip time measurement will be used. At least it will be used in the congestion avoidance algorithm of TCP. So the round-trip time of TCP is actually not really a great number, and this will have impact on the throughput. So, any questions on the standard stuff till here? Anything?
Okay, one question is, when you use frame aggregation, the transmission time becomes longer and the chance that one frame gets corrupted gets higher. So the longer the frames are and the higher the throughput is theoretically, the more rises the chance that the frames got corrupted. So what about retransmission? Do you have some selectable retransmission that you only have to retransmit one part of the whole aggregated frame, or how do you cope with this problem?
As you see, as I told very shortly, The 800.11e standard will give the new method of block acknowledgements. There you can acknowledge a bit mask of every frame you have transmitted here, here and there. And so when only one frame is corrupted, you will only retransmit this frame, but not all. So this is actually not the real problem for more the increased delay. But if you have a very noisy link, you will run into really troubles because the block acknowledgement, at least at 100.11e, is still a lot of overhead. At 100.11n, it's a bit better. You have no separate packet. They can be included in the normal Wi-Fi header. So, yes, this won't be it's quite okay. Further questions? Okay. Okay, half an hour passed. Let's go on. A bit slower. Okay, as I told you, the assumptions taken in the Wi-Fi standard does not really reflect two-user scenario on a point-to-point link, and also not really the situation on a mesh network when you use a shared channel. So at least the collision avoidance and the quality of service techniques look like as if you could get some performance out of these by optimize the values. The first one, perhaps the interframe space. This is the access delay in front of every medium access. It should be quite easy to optimize this. Just make it really small, because there's no use for traffic differentiation on a point-to-point link. You can do it on higher layers or somewhere else. Okay, and this will save you at least one time slot. It's not much, but it is at least a bit. On a 54 megabit link of 100.11a, it's 2.45%. If you, it's perhaps 1 megabit. It's quite nice. This number will increase if you use a new standard of 800.11n. There it will be nearly 4%. This is because the time and the interframe spaces and the timeouts stay more or less the same in this standard, but this, you will send more data at the same time, especially with using MIMO techniques. You can send 4 streams of data at the same time. So the efficiency between the time you're actually sending and the time you're waiting on your medium goes dramatically down. And so even this one very small time slot can give you an impressive performance increase. Using 4 streams at 800.11n will give you 5.25%. This is, I think, it's beginning to get interesting. As I told you, the CV max value, you can set it just to the CV min value. It doesn't, it's not really needed on point-to-point links. So the first interesting part, the CV min and the TX op limit. Both can be optimized, and when you optimize both, here you see the CV min value. It's always calculated 2 to the power of n minus 1. So you have always powers of 2 in the range of your random numbers. You can have 2 to the power of 1 or 2 or 3 or 4, resulting in a range between 0 and 8, 0, 8, minus 1, and or 0 to 16 minus 1, and so on. On the other side, here are the different times for the TX op limit. It's just in seconds or in microseconds. Oh, I think you cannot read the numbers. Even I can't read them. Let's look at the PowerBook. First, when we don't use any optimization, when we just use the 800.11e parameters like the normal standard of 100.11a, b, or t. The throughput you can see here is not really great, but you will see if you use longer times for the transmission opportunity, the throughput will increase. But it won't increase until the maximum value of the TX op limit. Somewhere it's an optimal point, and afterward the transmission, the throughput will decrease again. This is mainly a consequence of the semi-min value, because wait, just another slide. It's also dependent on the distance of your link. The throughput, if you have longer links, you have to adapt the time slots and the interframe spaces, and the result will you just see on this both slides. The graphs will change a bit, and the optimal points of throughput will also change. When it was, for example, on the short-range link at a min value of 3, and as you see here, let's choose perhaps this green line. It's at a min value of 3 and an TX op limit of 2 milliseconds. You see an optimal point, a maximum. There, on a longer link, this will change. The optimal time for the TX op limit will here be at 4 milliseconds. As you can see, it's quite complicated to find the optimal point or the maximum for all this. This is because when you have a long TX op limit, both stations will access the media for a long time. And the CV-min value will give you the probability of a collision. There could be a collision somewhere, and at this point, both sides will both lose the data, because both are sending, and at this point, no one will hear the other side. If you have a long TX op limit, you will lose a lot of data. If you have a short TX op limit, you will lose only a few data. So it's clear, if you have a really long TX op limit, you should increase the CV-min value to decrease the probability of a collision, because when then a collision will occur, you will lose a lot of data. So if you just choose on this graph some points, if you look at this is normal 800.11g or a, really unoptimized. If you now find the optimal point in this diagram, perhaps will be this line at CV-min value of 4 and a transmission opportunity of 4 milliseconds, you will see it's a quite big number at nearly 15% more throughput. That the increase of delay, it's up to you if you can live with this optimal number, 4 milliseconds. If both access the channel, you will actually have a delay of 8 milliseconds. I think for normal operations, it's still a good time. And Okay, wrong. wrong. The first number is optimization between when TX up limit is 0. It's this bar compared to that bar. When you just change the CV min value and let the TX up limit time stay the same. So you can see a 15% increase, and if you do an overall optimization from there to there, you will even get nearly 30% more throughput, and the delay is still acceptable, at least I think. This is nice. This was UDP. Using TCP is quite more interesting. If you just do some stupid TCP tests, not using UDP, just replacing the protocol, you will see the throughput is nearly 25% behind UDP. That's interesting, but we will remember, as I told earlier, it's a problem with the delay spread on this Wi-Fi channel. And the problem with the round trip time, I have to speed up a bit because the time is running. Okay, the first idea how to solve this, okay, use another channel, use it like the normal Ethernet, build a full duplex point-to-point channel using two separate channels, one for upstream, one for downstream. This actually will increase the amount of hardware you will need and the amount of spectrum to the double. As you can see here, a small test bed. We can see here two hosts communicating with each other, a router for separation the traffic flow from host 1 to host B, host 2, and host 2 to host 1. You could imagine the traffic will flow there, and backwards it will flow there. It's quite easy. It was implemented using normal Linux and Citrix PCs with Aceros cards, at least the cards you understand, 811A. As I told you, this will double the performance. Okay, nothing special. It will also solve the contention on the Wi-Fi link. Okay, nice, but what will mean this? And it will open the door for some optimizations. Okay. So you're now alone on your medium. Every node can more or less send at every time they want. So you can reduce the CV min value to a minimum. What is the minimum is a bit a problem. If you do it with Aceros, you cannot set it really to 0 or 1, because then the Wi-Fi card will restart every time. I don't know if this is a bug or a bug in the hardware abstraction layer or something else. It's just occurred, and I don't know why this happens. But in theory, you even could this value to 0. The TX up limit in the standard has a maximum of 8 milliseconds, and you can set this to the maximum. Okay, using an unidirectional TCP stream. As you can see in this graph, this is the normal one channel using with 2 users and used in a shared way. You have, as you can see, again, this optimal point of here for TCP and takes up limit of 1 millisecond and a CV min value of 4. It's quite slow compared to the other bars. This is the throughput you can get on the forward connection of a TCP stream when you use a separate channel for forward and backward connections. You can now get even more than 40% improvement. Sorry. And yes, it's only 25% to compare to an optimized shared channel. The difference is just in one point you use the old legacy channel, you're about here, to the optimal point of there, and in the other value you compare this value with that value. Unfortunately, this improvement, more than 40%, which is quite impressive, won't be usable if you have two TCP connections flowing in opposite directions. There you will again find this degeneration of throughput. This again happens because there are TCP data segments, rather large packets, and TCP acknowledgement segments, and they interfere with each other. So it's quite the same like on a shared channel, that they both stick in a queue and the acknowledgement get delayed, and TCP is very high. The result will be really high affected by delaying the acknowledgement. You can even simulate this just by using Linux net filter and tagging TCP acknowledgement packets and delaying them with the network emulation principle to a random number. And then you will see that the throughput of TCP will decrease dramatically. Okay, but if you look in literature, you find some interesting papers on how to solve this problem, which is called the TCP ACK congestion. The first one is just, as you might perhaps remember, the TCP acknowledgements acknowledge the latest packet they have received. And if you look in intermediate queues, there might be more than one acknowledgement for one TCP session. And so at least one packet will be redundant, and the queue can remove this acknowledgement. It's quite a strange concept, but it seemed to work, at least in the papers I've read. Another concept would be the ACK prioritization. I implemented in this method. It's just, again, using TCP net filter, taking the TCP acknowledgement segment and put it in the higher priority queue. As you see at the 800.11e standard, you have 4 priority queues. Now you don't use it for voice, video, background, and best effort differentiation. You now use them for normal flows and high priority flows. And the high priority are the TCP acknowledgement segments. It was a bit difficult to implement this, at least on the slow Cypress PCs, because they ran out of software interrupts and slowed down dramatically. But at least another test with a bit stronger PC showed 5.2% increase in throughput. This might be also too small number, and should be again tested with a really high-speed PC or 2 high-speed PCs with Wi-Fi connection, because it's at the moment not the best implementation to do this. And there's a really cool way to do this. It's called ACK congestion control, where you don't acknowledge every data segment, or nearly every data segment in a TCP window, but you can control when acknowledgement for TCP frames can be sent, and when you experience there might be congestion in the network, you decrease the number of acknowledgements you will send. This will have a bit an impact on throughput increase and decrease of TCP, but it will at least not suffer so much from the situation found on the Wi-Fi link. And now, shortly, the conclusion. Okay, you can, as I showed you, you can use 802.11e parameters on a shared Wi-Fi link, and you can increase the throughput significantly. It can be up to 30% for UDP. So it would be nice to have it on a point-to-point link. And the other solution, if you also want more throughput for your TCP flows, and the most packets in the internet are TCP, you can use the other idea and increase at least 40 or 26% for your TCP flows. And if you have a situation when there are a lot of traffic in one direction and in another direction, you can use this prioritization. Perhaps you will implement it a bit better than I did and get more than these 5.2%. If it's so, write me an email. And okay, this for that. But the main idea behind this, as I showed you, it's possible to do some optimizations and you get a real significant increase in throughput. But you will have to use a second channel. This is perhaps really expensive. And so there is the main idea behind this, to use this within a mesh network. But not within a mesh network like the Freifunk.net people using the same channel for every link between the nodes, but in a multi-radio, multi-channel mesh network, so that you can easily implement this, even if this leads to a bit a strange and asymmetric routing, using on the forward direction perhaps 1 or 2 hops, and on the backward connection you might use 5 hops and so on. In the normal internet, every scientific paper will say this is a really stupid idea. You should use the same path in the internet for forward and backward direction. Okay, it's not the reality in the internet, and in the wired internet perhaps it's also not really interesting. But at least they will tell you this. But remember the OLSR in later, I think for some years, 2 or 3 years, they also used hop count as a primary routing key for building a path from one node to another, but they soon realized this is not really a good metric for your routing. Perhaps it's better to use the expected transmission time between 2 hops, between 2 nodes, and not really the hop count. So the main problem will to be in the future to find good pairs of different paths between 2 mesh network nodes who have an equal transmission time, or an expected equal transmission time, and there to use this idea to separate forward and backward direction to get this improvement without the high costs, as I was showing in this test bed. Okay, I already implemented some parts of this, but it's not really quite stable or working yet. It's primarily intended to use OLSR and to do some extensions to have 2 pairs for 2 paths, or a pair of 2 paths with equal time. Perhaps we will see in the summer at the camp more details on this, and if it's really working or it was really a stupid idea, we will see. So thanks for listening, and we have only 5 minutes for questions.
Thank you for your talk. I asked me if there are, why are these parameters fixed? For example, I would try to add an adaptive strategy that depending on the traffic that both sides see, either symmetrical or asymmetrical or UDP or TCP, I would adapt the parameters to the optimal solution. So you could even change the protocols. I'm not a Wi-Fi expert, but you could do a lot of optimizations on the fly if you have an adaptation strategy.
Yes, you're right, you can do this, but at the moment I didn't implement this because I need some sort of information transport. Because normally when you have point-to-point link, you need the measurements of the other side also to give good decisions or strategies for the traffic. So you need communications between both sides. And how often do you communicate? This is also the next optimization problem. You cannot just for every packet you send another packet indicating I have sent a packet. So what's a cool way to do this communication and how often you will do this? At the moment I don't know, but you're right, this would be another cool idea to do on-the-fly optimizations. But we will see, not at the moment. Any questions left? Oh, okay, one.
Hello. What hardware and Linux driver do you use for the experiment on your experiment on double WLAN experiments? What hardware and Linux driver do you use for 802.11e?
And you want to know which Linux drivers I use, or
yes, or which
Wi-Fi?
Yeah.
I normally use Ethernet cards. The newer ones, which support 800.11a, and the normal Wi-Fi driver, the normal HAL driver, not the open HAL driver, and yes, okay, the latest stable version. Not there are several branches in the subversion, but I normally use a normal branch.
Okay, thank you.
Okay, if there are no questions left, I would like to say thank you to Achim Friedland and thank you for listening.